again, nice to see you guys all. Add yourselves to the quick reports if you got something. There's not really too much on the agenda for me today, as far as things to talk about. I don't know. How about today? Let's just do a quick round of everybody and see what everybody's up to. It's been a while since we kind of done that. Sound good? How about Dieter? You're on my screen first, if you don't mind.
Yeah, I'm literally just wrapping up all the loose ends. My project ends on Monday. So I hope to get the version 1 out for EMG3D and a revamped docs and website and all the things, so I can leave it a bit less attended after that, hopefully. That's it. Tuesday, I'm going to start more in the direction of data assimilation for reservoir modeling in the Delphi consortium. And with some other things, I'm not yet 100% sure with TerraSys, a small company from Germany. So we'll see how that new phase goes.
Interesting. Are you still going to be able to keep up every week with us?
I think so. So it's going to be 3 days a week at TU Delft, just another section in the department, and 2 days a week for this company, but it's remote. So I stay where I am. Yeah, I hope so.
Cool. John, what have you been up to?
Yeah, I've been tackling the merging main into simulation MT right now. Yeah, ultimately to get tiled all brought in, or main all brought into the simulation or the tiled simulations. Yeah, so just picking away at that slowly here. And I went on a little bit of a tangent and looked at that PyAMG solver, or that multi-grid solver. Yeah, for the big problems, it doesn't take up too much RAM, but it's still much slower, like over a couple orders of magnitude slower than PartISO. So I don't know, maybe there's some options that you can play around with. I was just a quick and dirty implementation, but yeah, good on RAM, but not so fast. Not much faster.
Interesting.
Yeah. And then I got a request at work to look at tiled tensor meshes. They don't really, I haven't really been able to sell everybody on the Octree fully. So they like the speed with the tiling, but they kind of want the tensor mesh stuff. So I'll maybe be picking away at that over the next little bit, if it's possible, or yeah, I might bug somebody to, if I get lost in the tiled code, just to see how it works.
What's the issue they have with Octree? I'm just curious of why they have their skepticism. Yeah.
I guess it's when the cells start growing. It's like, yeah, there always just seems to be a distinct boundary. Like it's distinct between the layer, or like in the Octree levels. Yeah, I've tried, or I haven't tried too hard, but I'm sure if you discretize properly enough, you can kind of minimize that effect. But everybody that I got to play with it, they're just like, oh, there's always, you can always see this boundary where the cells change. But yeah, that's mostly on DC though. I've had really good luck with the MVI stuff. No one really complains about the Octree on the MVI, but the DC, it seems to be a little bit of an issue.
Yeah, no, like the potential fields works great, but yeah, I can see what's happening with the with DC. It's true. Yeah. But yeah, like maybe there is some good practice to implement for that for the Octree.
Yeah, well, I think like Dom and I did a test set together here, or you were involved there, Thibault, on that monitoring, the DC one, and those Octree models look pretty good. I thought, like, didn't really seem like there was too much boundaries at the Octree levels, but yeah, I guess playing around with it enough, people are just like, eh.
I think what's my feeling is that they're always pushing too hard, the misfits. And then that's when you start seeing the Octree changes.
That makes sense. Yeah.
Yeah. I mean, I can tell you right away, like the tiled on tensor is going to be messy because you can't nest anything, right? So you start doing partial volumes and all that. I don't know.
Yeah.
I would vouch for them to get a better handle on Octree instead. I mean,
Yeah, I'll still keep kicking at that horse for sure. But
were they not like impressed by the savings? Because you got sort of where those corners are in the mesh, and in Octree it gets to be not very populated with cells, but when it's tensor, you got these long, skinny,
like prisms, yeah.
Yeah, and they weren't. I think also for EM, maybe like you kind of run into that aspect ratio of the cells, and you might not be solving it as accurately there. Somebody correct me if I'm wrong, but I thought there was.
I think Lindsay saw some of that in our CSCM comparison, that she just couldn't get it down with the Octree to a comparable error level as with the tensor mesh because of this 2:1 ratio.
Like I think I've said it before, but the UBC DCIP Octree UBC code, like the commercial one, cannot handle non-cubic cell. Like you can create a mesh with non-cubic cell, but it's gonna create massive artifacts. And I think there is maybe something in the gradient, or I don't know what's really happening. But like, yeah, like the UBC code with when you put like cells that are non-cubic, you create. I had experience where it created massive artifacts that disappeared when I was putting cubic cells.
But how non-cubic did you go?
Or like a ratio of like even like 1 to 1.5, like something like ridiculously small ratio, and was like, yeah, no, that's I could not use it with non-cubic cell, basically.
Okay.
Like
that's interesting. Like I might try out some testing on that, because we made some improvements to that code. Nothing related to what you're talking about, but yeah, I'm kind of in it right now, so I might be able to just try something. Was there a particular geology? Was it real data? Was it synthetic?
It was real data, and like I inverted with like cubic cells it was a very big survey. That's the thing too. So I was trying to gain on like lateral thing extra. Like my electrode spacing was 50 meters, and like line spacing was 150 or something like that. And I was trying to get it a little higher in terms of like the across line to gain a bit, because like with a cubic cell, I could only go for, even on the cluster, I could only go for 25-meter cells. So only 2 cells per electrode spacing. So like the short ones were not that good, but I could not more, and I was going over memory, and the inversion was already, even with the 25-meter cells, the inversion was taking like 2 weeks to run. So it was like a big one. So I was trying to increase a bit, just in like, I think I went like 12.5 and like 20 meters, something like that. And he was just putting massive, and suddenly massive conductors appeared between lines. And I mean, this was not, and those features were not in the cubic cell response in inversion. So
okay, yeah, that's interesting, because I inverted Mount Isa with the latest code. I guess it must have been like 8 months ago or something. And I remember having, I'm trying to remember if I made cubic or non-cubic cells when I inverted that, but I might go back to it. Yeah, so we've been playing around with sensitivity weighting.
yeah, but Dom, I want to go back to what you were saying for the tensor and Octree. Like what you said, you cannot do something with tensor that you can do with Octree, or something about the volume, but I could not understand what you were saying. I'm sorry.
I think you can do it. It's just you need to be careful on the when you do your projection, right, from the global to local.
Mm-hmm.
And I think Joe, maybe with your new interpolator, that can possibly do it. It will be a little bit slower to generate them, but it might work. Yeah, it might work. It's just it's a bit messy, because your nested meshes are going to have some it's not a one-to-one interpolation. Yeah, because exactly. The cells are not going to be overlapping well, right?
The volume average operator should work for it. Like it's tested against it, it should work for that in general.
Okay, yeah.
Though, I mean, I don't think there'll probably be some small artifacts and stuff from the overlapping cells. It's not as clean as the 1-to-1 ratio from like Octree nesting, like from nesting them as far as tiling. But it'll work. It'll still be volume averaging.
Right.
guess that's, yeah, about all that I'm working on. And yeah, Dom, I'll be getting onto the subtiled, or sorry, the VTAM styled survey, subtiling. Yeah, I just, we're moving offices and just got my cluster back up and going. So good to go.
Yeah, I still need to finish that example sort of.
Not to worry.
Ben is working on working on it right now, using the new implementation. So we'll be testing it on our side first, but I'll try to get it to you by the end of the week.
Radham.
Okay. Devin, how are you been doing? What have you been up to?
I got a few things. We're going to do a big release of the proprietary software stuff that our group does. So it's not really related to any of your things, but some stuff that might be interesting is that we've been playing around with different sensitivity weightings for DCIP octree. And we've also been investigating our time domain EM octree code. So by kind of identifying maybe issues, let's say imperfections, we're really kind of trying to zero in on kind of what's the best way to, I guess, define sources, or kind of like these little details. And because we're not worried about being able to solve the system a bunch of different ways. We just want to find the best all-purpose approach for simulating. So some interesting things have come out of it that maybe will end up getting adopted into SimPEG. We've been working on this MDRU project with Mag and Grav, Thibaut and myself, and that's been pretty fun. And playing around with kind of trying to remove a background or a regional contribution and then inverting locally. So we still have some questions, but the mag seems to be giving the good results. The gravity is very sparse and kind of difficult to work with, but we're moving along in that. And then when I can find time, more doc strings. So I've got enough to keep me busy.
Oh. Okay. Ben, what have you been up to? Anything exciting?
Not too much relating to SimPEG. Yeah, working on Dom's, refactoring Dom's GeoApps package. And yeah, I did finally kind of touch some SimPEG code recently, but yeah, just on our local tiled simulation branch, which maybe one day will get pushed, but keeping it local for now. Yeah.
Cool. Sharon, have you been up to with SimPEG stuff?
Yeah, last week I just I did some minor revision for the depth weighting according to you and Dom's comments. I think it's good to merge in the main branch. What do you think?
Yeah, that's pretty good. Do you mind? I think the only other thing is we need to write a test that does it, like a test function that runs it through like 1D, 2D, 3D mesh, things like that. Just simple, make sure it works.
Okay, I see. So and test files in the test folder.
Yep, you got it.
Okay, I can do that.
Cool. Dom, you're up next on the screen.
Yeah, well, we did. We worked with Sharon, right, and yourself. Try to get this general distance weighting function looking pretty good. Otherwise, I started looking into regularizing the different like functions of the model in terms of like amplitude right now. It's a bit more complicated than I thought, just because the way cell weights are applied, right? We're doing the mapping of weights. You kind of want to have two layers, not just applying the weights on everything. Anyway, it's a little bit more complicated than I thought. So I'm tinkering around, try to see how we can, maybe add another layer or refactor what we have. That's what I'm up to.
Do we did you give any more thought to the, so when we're, with regards like to the depth weighting stuff, when we, you and I were talking about the, like the volume normalization part of it, you know, have you given any more thought to that? Like in context, so when we have cell weights on like the regularizations, right? On all of the, whenever they're implemented, I believe like we've multiplied by volume afterwards because we're doing the integral of that function. It happens everywhere except for when you have the update sensitivity weight thing. The sensitivity weight all like includes the volume term in there. So kind of you have to take it, you have to use like a special regularization function, I think, when you're using that because you can't use like the Tikhonov regularization and other stuff because of the volume. Like the volume gets multiplied essentially twice there. So
it's a bit worse than that, unfortunately.
Yeah.
Because the small, right, in the Tikhonov basically always multiplies by reg mesh volume, even if you have, if your cell weights are normalized or not. So we need to change that priority because it's different behavior. Basically, if you use simple or Tikhonov, it's a bit of an issue. So we should uniformize everything. They should all behave the same.
Mm-hmm.
And then, yeah, basically in the directive, denormalize the, or, divide by volumes beforehand so that when it goes into the regularization, it multiplies it back in. I think that's probably the easiest way.
Yeah, that would be my bet as well, just to have everything come in and not expect things to be volume, like volume. We'll handle the volume term. I'll just make everything.
Yeah, and make it clear that the weights should be volume normalized, right? If you put anything in there, it should be volume normalized. Yeah. Maybe that, John, that's something you should look into too, right? Like in your code that you're using, which regularization you're using, basically, because that might affect you big time.
Yeah, well, I've got everybody over to sparse for the
Okay.
But yeah, I remember we had this chat with Tikhonov, and yeah, this is pretty bad in the Tikhonov.
Yeah, so we should create an issue. I'll create an issue now to make sure that we have a flag.
Like there's a subtlety because like let's say if you use the sensitivity weighting, for instance, then that sensitivity actually includes the volume term, I think.
Yeah, that's what we're saying.
Don't want to multiply the volume.
That's right. So we need to make sure that we need to assert that if someone puts in cell weights, they need to be volume normalized, all right? So that way we handle the volumes ourselves inside the regularization.
I see. So in the regularization, you always multiply the volume. So it's the user's job to divide your weights by volume.
Exactly.
Every time.
Or if it's like, for instance, for Shalom, that weighting function, like you don't multiply that by the volume, right? Like, because that's just a function. So it's just you have to make sure that your things are volume normalized, that it's not dependent on the volume of the cell that you're doing it on.
Yeah.
Okay. Thibaut, you're next.
Not much in terms of code. I've been mostly focused on several case studies at the moment and dealing with real data sets in very green area that we don't know much about, and see what I can do with PGI in those areas.
Interesting. Cool. Sagi, we've just been going around, obviously.
I don't have nothing particular. I'm actually trying to invert the remote sensing data using SimPEG. I actually wrote a small flow modeling code, and it's actually basically 1D. It's very similar to airborne inversion. So you take account the remote sensing data, which is a time series, as like a 1D inversion, but you got zillions of points. So you can set it up as a 1D problem. And the goal is actually recovering the head variations in the aquifer system. So I'm pretty promising. I'm not sure whether that's going to work or not, but if that's working, that'll be actually quite impactful, because you can actually get the head data from the remote sensing data, which you can get every 6 days. So yeah, anyway, it's working on quite different problems. I am slowly moving on with the CSAMT inversion. So we're going to test the EMG3D implementation in SimPEG using the CSAMT data. I got one data set from Doug, and I'm going to get another data set from Nick. So yeah, it'll be interesting to test that code. And one thing that we're going to try a little bit new with the EMG3D is the anisotropy. So we're going to invert for at least a horizontally isotropic, but an isotropic resistivity. Not sure whether that makes a big impact to the CSAMT inversion or not, but anyway, we'll test it. So that's sort of what I'm doing.
Okay. And then me, I've been going through working on one of my own small projects simulating electric fields in the skull, which is kind of interesting. And then I've also been going through the EM1D stuff as well, trying to look through it and make simplifications where I can and kind of see what's happening, and working towards getting that time domain one working much quicker. I'm working towards it, getting there. I've just kind of, my only handle that I don't have on it is I'm not sure how much memory it takes up already in regards to, okay, if I want to store a few extra things, is it going to be that impactful on the memory footprint?
I think it's pretty minor, Joe, but the memory consumption is pretty minor. I think actually increasing memory consumption is kind of fine, in the sense that if you can actually improve the time, yeah, like usually even my laptop is pretty fine to work, like invert the large scale at 1 year data. So no, it's not even using, like I got 8 gig. It's not using 8 gig, so it's pretty small.
Okay, then I'm going to keep chugging away at it. I've been making simplifications to it, things like, just looping, like getting do a loop through the source receivers, calculate all of their offsets, all of their coefficients ahead of time, just do that once, and go through and describe all the unique frequencies and call that RTE function once, things like that.
Are you thinking about like let's say you got 1,000 soundings, and are you thinking about handling those 10, like 1,000 sounding once? Is that what you're thinking, or you're still are thinking at the level of a single sounding?
I'm still at the level of like a single sounding, but also like what you're talking about, like 10,000 soundings, like things like that. I mean, if they're all over, it'll right now I just have it kind of going through and looking at the unique source receiver offsets and just modeling those for each sounding. So hopefully we can do that. But at the level of like, the multiple, like the stitched 1D stuff, you can at least take advantage of like, calculating all those coefficients ahead of time instead of repeatedly calling them.
Right.
Just getting frequency stuff.
If you ever have, or anyone has a huge airborne inversion job or project or something, I think it might very well be worth to try and design a filter for airborne stuff, because I don't think any of the filters we use was designed having airborne in mind. So we could probably get away with much shorter filters specific for that topic, which would then weigh in heavily on the runtime.
Mm-hmm.
Yeah, we talked about that with Joe.
Okay.
I think that's probably sort of best part that we can actually make, because if you can reduce the, I think we're using 101, and I'm not sure what's the time, but if we can add 101 filter to 50, that's factor of 2. So yeah, it'll be great if you can do that.
So anyway, that's what I've been up to.
I just wondering, it is a good idea to add something in the depth weighting results in the tutorial gravity.
I think if
I can show the results for the with different exponent parameters and something.
Speaking of that, Xiao, did you like an initial depth weighting implementation? I think they actually solved like a simple like least square problem, because you got a couple of unknowns, right? Like you don't know what exponent you need to use. You also don't know like that there's a constant factor Z0 needs to be into that depth weighting. So I think they actually just, I think in the beginning they got sensitivity kernel, then they kind of solved a simple problem to figure out what that optimal parameter. Is that what you have done in your implementation, or it's basically just an input like that Z0 an exponent?
I think this function can do the both. We can use the sensitivity curves to determine the exponent and the constant parameters, and we can also input some other parameters what we want.
That's cool. Cool. And related to that, I thought that what the projected Gauss-Newton that we're using, it's kind of fine, but still, I compared the Raglan inversion result with the UBC code, and I found it was pretty good, but especially where you have, I think it's actually happening when your update are negative, but then projected Gauss-Newton kind of put that into a positive value. And I think it kind of generates a weird, very sharp boundaries. So I'm not sure, I think we spent quite a bit of time to actually modify that projected Gauss-Newton, but still it seems like it's not as good as the UBC code, which uses the slightly different method. I think they're using the log barrier, I guess. So I thought maybe that's something worthwhile to think about implementing, especially for that positivity constraint. I think in general that the projected Gauss-Newton is kind of fine, but I think if there are if the projection has a lot of infeasible sets, then that could still make a problem. I don't know. That was just a thought, but yeah, Xiao, you're implementing the old kind of style things, so I thought it's probably worthwhile to think about that.
You just project it to 0, right? It's it doesn't move it to positive territory.
I think that, are you talking about the log barrier method, or
no, the projected?
Yeah, the projected Gauss-Newton just projected to 0. And I think,
to the bound, yeah.
Yeah, to the bound, and then it uses, if the values are on the bound, we use the first order mathematical update for those values on the bounds. So which we follow whatever the methodology is. So I don't know, we can make a big improvement there. The another option was I think that UBC code uses this log barrier method, I guess.
Not anymore. No.
Not sure.
Yeah, Ben did it a long time ago.
Oh, I see. So that it uses the projected Gauss-Newton now.
Yeah.
Oh, okay. Then never mind.
Yeah, log has been abandoned probably since V3 or something.
Yeah.
Oh, maybe then. Yeah, that's not worthwhile then.
Well, what I know from the log barrier, it's just it's slows down. Like the late iterations just don't update very much, and then it's hard when there's a bunch of stuff near the bounds, right? You get like small updates for stuff. It just slows down when there's a lot of stuff at the bound.
Okay. Never mind then.
I mean, there's no reason we couldn't have like a log barrier method in there if people wanted to use it, like that minimization function in there. Like, there's no reason we can't have it as another option, but.
Isn't it just like inverting like susceptibility and log? Wouldn't that do the same thing?
No, no.
Just avoid to go negative.
No, I think it's
You have,
different.
you have this barrier term that essentially like makes artificial walls on the boundaries. You can imagine, like, if you know, thinking about a minimization function as a bowl, it adds these like really bounds, and then as you get closer to it, it goes up, and then
it's harder and harder to cross over, right? Exponentially harder.
And then like as you iterate, so it starts as like a smooth boundary, and then it starts like you reduce the parameter and it goes sharper and sharper. That's what happens. Like it's just a nonlinear regularization that's added to it.
If there is time, I thought I'd quickly bring up the question I asked about plotting in discretize. If my assumption is correct, or if I missed something, if we could change it potentially or not, or.
Yeah, so I took a look through it, and I kind of went through the tensor mesh code at least. I think what we could do, like what should probably happen is that when you're plotting like those space values and things, we should do a slice. We should slice it before we average it to the cell centers, because right now everything gets averaged to cell centers and then sliced along the axis, which is what's taking up a lot of memory when you do that. So it'd probably make better sense like to just write it where it slices those faces and edges first and then averages it, or it slices those faces.
Yeah, that's true.
Faces, edges, nodes first.
That would definitely alleviate the memory consumption. But would it make sense to plot the edges at the edges?
Yeah, so that's one of the other things that I talked about, that garage shading. So if you do that, like it should have the values at those edges be correct. And then it's kind of like linearly interpolated through the cell.
When we are at the edges, yeah. That's correct.
When it's at the edges, it's the correct value, but it just interpolates it through the cell as part of the plotting routine.
Yeah.
So that's why, like, I think that would probably be the best route, but then I don't know what to do about it on a tree mesh, because you can't just slice it ahead of time.
You cannot. You cannot take out a. No. I also don't know what would happen at the cylindrical mesh. I don't know how that works.
I don't know. I'd have to look at it either, but we could at least get it better for tensor mesh. We can improve it for that. Say like it pretty well. The on tree mesh, right? Like you could do the nodal. I think you could. I'd have to look, but like you can't, because things aren't regularly shaped. So you can't take advantage of those slicing operations. Or like,
yeah. Yeah, it's nothing urgent. It just came up because some plots we did and then compared. I think I created a P color mesh manually and then plotted with discretize, and then you can see there are tiny differences because one is interpolated to cell center, and then I just remember me that I had a couple of times I could compute the electric field, but when I tried to slice to plot it with the slicer or plot slice, then it would say memory error. And
we should definitely just slice it ahead of time on the tensor meshes. Anything else anyone wants to chat about? If not, I don't mind keeping things lighter.
Sounds good. I'm still curious though about the iterative solver that you talked about, Joe, right? Why is John getting such a slow solve compared to what because you were solving for 3 million cells. I mean,
yeah, like 2.7 million or so. I don't know.
in like 18 seconds. That sounds pretty remarkable.
Like, I don't know. I'd have to look at what he was doing and what the
Right.
system was.
Yeah, I did have, like, it doesn't take the multiple right-hand sides, so I have to loop over the right-hand side. So that right there kills quite bad.
Of course.
But that's the thing, though, when you look at the Paradiso one, they're actually looping over the sources as well. So I thought, oh, maybe it can get away with it, but it's not the same, though.
Yeah, but they probably don't have to make the full, even though they loop over the right-hand side, right?
You just do it as a matrix, as a matrix operation.
Well, I thought that, yeah, there's a for loop right through it, through all the sources. If you look at in PyMat Solver, I thought it was PyMat Solver.
No, in Paradiso, you pass it multiple right-hand sides and it's able to solve them all.
Oh, okay, I see. You're just passing it until it's okay.
Yeah, like it does it at the C level. I don't know. There might be a way that we can. Yeah, I don't know. We'd have to see. Is it like it's the iterative solvers that kind of? Yeah, we could probably check it out.
I'll push it to this branch that I made for that Neil guy. I'll just add it to there, and you can take a look.
Yeah, Dieter, have you messed around with that PyAMG, with the algebraic multigrid solver package?
No, no. There's also the PyAMG, or is it this one, the algebraic multigrid solver? And
yeah,
no, I didn't look.
Yeah.
Yeah, I tried. It works like for if you're using homogeneous value, it works quite well. But once you introduce an air cell, I think it just like gets so poor. So I think I kind of gave up at one point, like because you actually do need more sophisticated, like that.
The thing is with multigrid, if it works fine, it works fine, and if it doesn't, it doesn't. So like the stretching, the thing that is implemented in EMG 3D, there's this line relaxation and semi-coarsening, because otherwise with anisotropy or stretched cells, you would very quick become very slow. So there needs to be just the pure multigrid will only work for very restricted cases. Yes. Yeah.
Does it have anything to do, like, how is it related to the condition number of the matrix?
I don't know. I don't have a matrix. As I don't have a matrix.
Yeah, I think that once you got a large contrast in your physical property, the condition number gets bad. So I think it's one reason. I think why that gets so poor.
Like there are many things, like in EMG 3D, if you make the air very resistive or the frequency very low, you will very soon go to never-ending land because convergence becomes very slow. So you can, for instance, at the moment, not use it for DC. We would have to implement additional things. So I think it's with a lot of iterative solver the case that you have to tailor them to your problem, whereas with direct solvers, they are much more robust and flexible.
Mm-hmm.
So yeah, I'm not surprised that with just a quick try, it's probably not very quick. Yeah.
And is that using multigrid as the solver or a preconditioner to
either? But usually
yeah.
I can use it as a preconditioner for any or many of the SciPy Krylov subspace solvers. But often I use it on its own.
Okay.
Yeah.
I had always heard that the best performance comes if you can finely tune the multigrid method, but if you don't have the time or can't do that, that using it as a preconditioner can get around some of the. Yeah.
Yes, particularly strong on isotropy or stretching, things like this, it can help.
Right.
But then again, it's so difficult. I wouldn't have few rules of thumb because you just have to try it. Sometimes it helps, sometimes it doesn't. Yeah, it's really tough.
Yeah, surprisingly, if I read the literature, people still use the Jacobi, and which is surprising, but it's probably working. I think the convergence gets poorer as the system goes large, but I think people still use it somehow, which I don't know how that's working. But.
Yeah, I don't either. Okay.
It's time to party, so what can I say? All right, see you guys.
But make the
Have a good
domain
day.
small and use the direct solver.
Yeah, exactly. Yeah. So far, that's the only solution. Cool. All right.
Well, but Sogi, when
Oh.
if you get the CSA-MT working, that could then also work for John and some MT work, right?
Yeah, I think so. The potential, John, is I think actually transferring EMG3D into an MT code may not be a huge hurdle, I think, because as long as we use maybe the secondary field formulation, I think there's nothing to change. We just need to change the right-hand side in the EMG3D. So I'm not going to do that, but I'm just going to test whatever existing code and the CSAMT example, which is much simpler. But I think what probably worthwhile to generate is a receiver class that can handle the impedance. So, because it seems like the typical system is Quantex system, and what they basically provide is the apparent resistivity and the phase from either ZXY or ZYX. So yeah, I think that's probably my goal. And as long as we can implement that, and I think from there, actually updating that into an actual MT code may not be a big kind of work, I guess. So there's a chance. And I think that Dieter's code is working like relatively high frequency. Let's say, I don't know, 0.1, I guess, for sure. But I think that's probably mostly the case that you would like to invert for a lot of mining, unless you go really, really deep like a mental. So I think it's in a practical sense for mineral exploration, I think that code could be quite useful. But anyway, that's just a thought that we have at the moment.
Yeah, I could be into that for sure. That's cool. We're actually doing some CSAMT ourselves now. I've got some good data sets that I might be able to use. Like, and we've like got all the wire paths taken out. Like we've collected like all the details so that we can simulate it in a way eventually. I was going to get there.
Oh, great. So you're actually going to look like, kind of record where the source locations are.
Yeah, exactly. Because we just had a project where we thought like the client thought it was going to be far field, but it turned out the ground was more resistive than they thought, and it was more into the near field. So you kind of need the source to find. But yeah, that's just one of the ones we have here that we were looking at.
Yeah, I was just kind of laughing because people don't record that source location. So, because the code they are using is the 2DMT code. So they don't really need to know where the source locations are. So a lot of historical data doesn't have the source location, which is like, I thought crazy. Anyway,
Yeah, just,
what gets better.
yeah, exactly. Far field example or far field assumption all the time. So.
Sounds good. Well then, see you guys all next week. Have fun doing your stuff.
Bye-bye. See you.
Bye.
See you later.